The universe is broken, not in a poetic way, not in a philosophical way, but in a measurable, testable, keeps scientists up at night kind of way. And after years of hoping somebody made a math error, a Nobel Prize-winning physicist just confirmed that nobody did. Adam Riess won the Nobel Prize in 2011 for discovering that the universe's expansion is accelerating, that something invisible and unexplained is pushing galaxies apart faster and faster. He called it dark energy. That discovery alone was enough to rewrite textbooks. But what the James Webb Space Telescope has shown him since then is worse. The numbers don't just challenge one theory, they challenge the entire framework we've used to understand the universe for the last 3 decades. And Riess, the man who found dark energy, looked at the data and said something no physicist ever wants to say. Our understanding of the universe may be incomplete. To understand what went wrong, you need to know about a number. It's called the Hubble constant, and it measures how fast the universe is expanding right now. Not how fast it expanded a billion years ago, not how fast it will expand in the future, but right now, today, at this moment. It sounds like it should be simple to measure. Point a telescope at a galaxy, figure out how far away it is, figure out how fast it's moving away from us. Divide one by the other. Astronomers have been doing versions of this since 1929, when Edwin Hubble himself first noticed that distant galaxies were racing away from us. And the farther away they were, the faster they moved. For decades, the measurements were rough. Different groups got wildly different answers. Depending on who you asked, the universe could be anywhere from 10 to 20 billion years old. But the broad strokes agreed. The universe was expanding, and the expansion was slowing down over time because gravity pulls everything back together. Simple, clean, reassuring. Then, in 1998, 2 teams independently discovered that the expansion isn't slowing down at all, it's speeding up. Riess led one of those teams. Saul Perlmutter led the other. Brian Schmidt was on Riess's team. All 3 shared the Nobel Prize. What they found was that some invisible energy, something with no known source, no known mechanism, and no known identity, was pushing the universe apart faster and faster. They called it dark energy, which is a polite way of saying we have no idea what this is, but it makes up roughly 68% of everything that exists. That discovery didn't break cosmology, it reshaped it. Physicists folded dark energy into their models, updated their equations, and kept going. The standard model of cosmology, called lambda CDM, absorbed the shock. Lambda is the symbol for dark energy. CDM stands for cold dark matter. Together, they describe a universe where 68% is dark energy, 27% is dark matter, and about 5% is the ordinary stuff. Protons, neutrons, electrons, the matter that makes up stars and planets, and you. This model predicted the expansion rate, the age of the universe, the distribution of galaxies, the temperature fluctuations in the oldest light we can see. It worked. For 30 years, it worked beautifully. Then precision happened. Riess and his team spent 2 decades refining a technique that uses a special type of star called a Cepheid variable. These stars pulse. They brighten and dim on a regular cycle, and the length of that cycle directly relates to how bright the star actually is. Henrietta Swan-Leavitt discovered this relationship in 1908, and it remains one of the most important tools in astronomy. If you know how bright a star actually is, and you can see how bright it appears from Earth, you can calculate how far away it is. It's like seeing a streetlight in the distance. If you know all streetlights are the same wattage, the dimmer one is farther away. Astronomers call this the cosmic distance ladder, because each measurement relies on the rung below it. Cepheids are one-rung. Type 1a supernovae, which are a specific class of exploding stars that all detonate at roughly the same peak brightness, are the next rung up. You measure the Cepheids to calibrate the supernovae, and then you use the supernovae to measure galaxies billions of light-years away. By 2022, Riess and his SH0ES team, that stands for supernova H0 for the equation of state of dark energy, had measured the Hubble constant at roughly 73 kilometers per second per megaparsec. That means for every 3.26 million light-years you look out into space, galaxies are moving away from us 73 kilometers per second faster. The measurement was exquisitely precise, less than 1% uncertainty. Meanwhile, a completely different team was measuring the same number using a completely different method. Instead of looking at nearby stars, they looked at the oldest light in the universe, the cosmic microwave background. This is radiation left over from when the universe was only 380,000 years old, a faint glow that fills every direction of the sky, a snapshot of the infant universe. The European Space Agency's Planck satellite mapped this glow in stunning detail, and then used the lambda CDM model to run the clock forward, calculating what the expansion rate should be today, 13.8 billion years later. Their answer came out to about 67 kilometers per second per megaparsec. 6. That's the gap. 73 versus 67. It doesn't sound like much, but in a field where measurements have been refined to less than 1% uncertainty on each side, a gap of 8 to 9% is enormous. It's the difference between a universe that behaves the way our physics says it should and a universe that doesn't. Cosmologists named this gap the Hubble tension. Tension, as if two friends were just having a polite disagreement. David Gross, another Nobel laureate, had a different word for it. At a 2019 conference at the Kavli Institute for Theoretical Physics in California, he told the room they shouldn't call it a tension or a problem, they should call it a crisis. For years, the most common assumption was that somebody had made an error. Riess's Cepheid measurements, taken with the Hubble Space Telescope, were done in crowded star fields. When you're looking at a pulsating star in a galaxy 100 million light-years away, other stars crowd around it. Their light can bleed together in the telescope's image. Maybe the Cepheids appeared brighter than they actually were because of this contamination. Maybe the distances were slightly off. Maybe the whole ladder was leaning to one side. This is where the James Webb Space Telescope enters. And this is where the story stops being a technical disagreement and starts becoming something that genuinely unsettles the people who understand it best. Webb sees in infrared. Its mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's. Where Hubble squinted at Cepheids through a fog of neighboring stars, Webb cuts through the clutter like switching from a security camera to a surgical microscope. It can look at a Cepheid variable star in a galaxy 130 million light-years away and separate it cleanly from the stars packed around it. The crowding problem that had haunted Hubble measurements for decades was, for Webb, barely a problem at all. In February 2024, Riess published the results. His team had used Webb to observe over 1,000 Cepheids across 6 galaxies, including NGC 5468, the most distant galaxy where Cepheids have been reliably measured. They compared every single measurement to what Hubble had recorded. The two telescopes agreed. Hubble's numbers were right. The Cepheids were not being distorted by crowding. The distances were accurate. The ladder was solid. Riess and his team rejected the crowding hypothesis at 8.2 sigma, which in statistics means there is less than a 1 in 100 trillion chance that crowding explains the discrepancy. Physicists confirmed the Higgs boson at 5 sigma. This result was more certain than that. The measurement error explanation was dead. As Riess put it, with measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe. Then, in December 2024, his team published an even larger study, the biggest analysis yet, covering roughly a third of Hubble's full galaxy sample using Webb data. They didn't just use Cepheids this time. They cross-checked with two completely independent methods: tip of the red giant branch stars and carbon-rich giant stars. All three methods calibrated against a galaxy called NGC 4258, whose distance is known from precise geometric measurements, pointed in the same direction. The differences between Hubble and Webb were under 2%, far smaller than the 8 to 9% Hubble tension itself. Xiang Li, a graduate student at Johns Hopkins working on the study, described it simply. The Webb data is like looking at the universe in high definition for the first time. Now, not everyone agrees that the tension is as severe as Riess claims. Wendy Freedman at the University of Chicago has been measuring the Hubble constant with her own program, the Chicago-Carnegie Hubble program, and her results using Webb data on 10 galaxies came in between 68 and roughly 71 kilometers per second per megaparsec, closer to the Planck prediction. Her team argued that the two methods least affected by crowding, the tip of the red giant branch and carbon-rich stars, give values consistent with the standard model. Cepheids, Freedman suggested, carry complexities that might introduce subtle biases, complexities related to their chemical composition, their surrounding environments, the dust between them and us. Every method is plagued by systematic errors, she said, some of which may be unknown. Riess's team published a rebuttal, arguing that when all three methods are calibrated the same way, they converge on the higher number. The disagreement is ongoing, civil, productive, and completely unresolved. Both teams continue collecting data. Both teams believe the other is making an error somewhere. And frankly, this is exactly how science is supposed to work when something fundamental is at stake. What nobody disputes is that the universe is not cooperating, and the expansion rate is only half the story. Because while Riess was confirming the Hubble tension from one direction, Webb was blowing open a completely different problem from another. Almost immediately after it began full science operations, Webb started finding galaxies in the early universe that shouldn't exist. Not metaphorically. According to every model cosmologists had built, there simply wasn't enough time after the Big Bang for galaxies that massive and that structured to have formed. The standard model predicts that tiny density fluctuations in the early universe gradually pulled matter together through gravity, first into small clumps, then into proto-galaxies, then slowly, over billions of years, into the large organized galaxies we see today. You don't build something the size of the Milky Way in a few 100 million years. The hierarchy of structure formation is clear about that. Webb found galaxies that didn't get the memo. Within weeks of its first deep field images, astronomers spotted galaxies at redshifts so high they dated to within 500 million years of the Big Bang. These galaxies were far too bright, far too massive, and far too well organized for their age. Some of them appeared to contain as many stars as the Milky Way, which has had over 13 billion years to accumulate its stellar population. These early galaxies had apparently done the same thing in a fraction of the time. It was like finding a skyscraper in a neighborhood where the concrete hadn't even dried yet. One galaxy discovered in early 2025, nicknamed the Big Wheel by researchers at Swinburne University of Technology in Australia, had a full spiral structure less than 2 billion years after the Big Bang. Spiral galaxies are supposed to be the product of slow, orderly growth over billions of years. Violent mergers disrupt spiral arms. Chaotic early conditions prevent them from forming in the first place. Thamiya Nanayakara, one of the researchers who identified the Big Wheel, noted that whatever process grew this galaxy either happened in a remarkably clean and orderly way, allowing it to keep spinning without violent disruptions, or the bulk of its mass formed right where it sits. Neither option fits neatly into the standard picture. If mergers built it, the mergers should have torn apart the spiral structure. If the mass formed in place, then something was funneling enormous quantities of gas into an organized disk far earlier than anyone thought possible. Either way, the Big Wheel is a galaxy that looks like it belongs in the modern universe, sitting in a time period when nothing that organized should have existed yet. A team at the University of Missouri went further. Using Webb's near-infrared camera and mid-infrared instrument, they identified 300 candidate galaxies in the early universe that were brighter than any model predicted. 300 objects that our framework said shouldn't look like that, shouldn't be that luminous, shouldn't have built that many stars in that little time. If even a fraction of them are confirmed as genuine early galaxies, the models of how galaxies assembled in the first billion years need serious revision. Some nuance matters here. Not all of the so-called impossible galaxies stayed impossible. Early Webb data was still being calibrated when the first headlines hit, and some brightness estimates were revised downward. A batch of the mystery objects turned out to be a completely new category that astronomers now call little red dots. Compact, brilliant sources that appear to be powered by enormous black holes eating surrounding gas, rather than by starlight from trillions of ordinary stars. And Katherine Chayefsky at the University of Texas at Austin led a careful study showing that when you properly account for the uncertainties in estimating stellar masses from fuzzy infrared blobs, some of the early galaxies shrink to sizes that don't necessarily violate the model. But not all of them shrink enough, and even the partial explanations open new questions. Supercomputer simulations from Northwestern University suggested that stars in the early universe may have formed in sudden, violent bursts, rather than at the steady pace we observe in modern galaxies. If a galaxy happened to be caught mid-burst, its youngest, most massive stars would be blazing at peak luminosity, making the galaxy appear far more massive than its actual total star count suggests. The most massive stars burn through their fuel fastest, so a galaxy's brightness is more closely tied to how many stars it formed in the last few million years than to its total accumulated mass. Catching it during a burst is like photographing a sparkler at the moment it ignites. It looks enormous, but the stick is small. This would mean the galaxies aren't as massive as they first appeared, which sounds like a relief until you think about what it implies. If star formation in the first billion years operated in a fundamentally different mode from anything in the following 12 billion years, then the astrophysical models we've been using to interpret all of Webb's early universe data are built on assumptions about how matter behaves that may simply be wrong for that era. Rachel Somerville, who studies galaxy formation at the Flatiron Institute in New York, put it this way: in retrospect, it's perhaps not surprising that things were different in the early universe, but the assumption that they were the same had been hard-coded into the models. Webb is forcing that to change. And here is where the two crises converge. The Hubble tension and the early galaxy problem aren't sitting on different shelves. They're connected through the same underlying model. Lambda CDM predicts both the expansion rate and the timeline for structure formation. When the expansion rate measured locally doesn't match the rate predicted from the early universe, and the timeline for galaxy formation turns out to be more compressed and violent than anyone expected, you're not looking at two independent puzzles. You're looking at the same framework, under pressure from two directions at once. Some physicists think the fix might be subtle. Riess himself has explored a version of lambda CDM where dark energy evolves over time, stronger in some eras, weaker in others. That would change the expansion history and potentially alter how quickly structures could form. But research by Ryan Keeley and colleagues complicated that idea. They found that the expansion rate matches lambda CDM predictions all the way back to the cosmic microwave background. If there's a break in the model, it's not in the middle of cosmic history, it's at the very beginning, in the physics of the universe before that ancient light was released. That constraint has sent theorists into increasingly exotic territory. Some have proposed extra dimensions from string theory, leaking gravitational effects into our observable universe. Others suggest a new class of particles that existed only in the earliest moments after the Big Bang and then decayed, adding a brief pulse of extra energy that kicked expansion into a higher gear. Still others have questioned whether gravity itself behaves differently at the largest scales. Each idea is speculative. None has strong observational support yet. All of them are being taken seriously because ignoring data that 2 Nobel laureates have spent decades collecting is not an option. Over the next decade, new instruments will join the investigation. The Vera C. Rubin Observatory in Chile is expected to discover roughly 300,000 new supernovae per year, vastly expanding the dataset for distance measurements. The European Extremely Large Telescope, with a primary mirror 39 meters across, will resolve individual stars in galaxies far beyond the current reach of any telescope on Earth. NASA's Nancy Grace Roman Space Telescope will survey a field of view 200 times larger than Webb's, mapping the distribution of dark matter and dark energy across billions of light years. Freedman said it plainly, "We've only scratched the surface. The path is clear, we're only just beginning. And maybe that's what matters most about this moment. Not the crisis itself, not the polite war between 2 brilliant teams. Measuring the same number with the same telescope and reaching different conclusions. Not the galaxies that refuse to wait their turn to form. What matters is that we built a machine, folded it into a rocket, launched it 1,000,000 miles from Earth to a gravitational balance point between the Earth and the Sun, unfolded its gold-plated beryllium mirror, segment by segment, in the vacuum of deep space, cooled its instruments to 40 degrees above absolute zero, pointed it at the oldest light in existence, and found something we couldn't explain. Every major leap in physics started exactly this way. Newton's mechanics worked perfectly until Mercury's orbit didn't fit. Einstein's relativity worked perfectly until it collided with quantum mechanics at the centers of black holes. Lambda CDM has worked perfectly for 30 years. The fact that it's showing cracks doesn't mean we were wrong to trust it. It means we finally built instruments precise enough to see where it breaks. The universe doesn't owe us consistency. It doesn't arrange itself for our convenience. It was here for 13.8 billion years before any human looked up and tried to make sense of it. And the most honest thing a Nobel Prize winner can say, after decades of work, after winning the highest honor in science, after watching the most powerful telescope ever built confirm that his measurements were right and the universe is still refusing to cooperate, is simply this. We may have misunderstood it, not because we were careless, because the universe is deeper than we realized. Somewhere, right now, Webb is collecting photons that left their source billions of years before Earth existed. Those photons carry information we don't yet know how to interpret. And the gap between what we expected and what we're finding isn't a failure of science. It's the sound of a new chapter beginning. We're not losing our grip on the universe. We're outgrowing the map we drew of it. And that's it for this video. Thanks for watching, and I'll see you in the next one.